Welcome back, Chemistry 30. This is the MS1.5 section looking at drawing Lewis structures again. In 1.3 we looked at it, and then in 1.4 we looked at electronegativity. Now we kind of take a step back and introduce something else, because we've been kind of going this at baby step pace to see how we do things. Then we're going to add one other thing, and that is calculating formal charges to see if the Lewis structure is valid for a particular molecule or ion, and then we'll be able to draw them more successfully, because there's one or two things that we kind of overlooked. So there's a further method that should be used to determine whether a particular Lewis structure is reasonable, and it involves calculating formal charges on each atom. And it's one technique that we can use to make this judgment. Formal charges is the difference between, this is a key thing to note, it's the difference between the number of electrons an atom has in the Lewis structure and how many it should have in terms of valence structures. So you may have noticed in a couple of these diagrams, especially with oxygen, you sometimes notice, well, it doesn't have 6 electrons in the structure. It has more or less. So we'll be taking a look at that and seeing how we can make more valid structures by looking at this. So first, it's important to understand the concept of formal charges. In a covalent compound, an atom shares some of its valence electrons to form bonds, while the rest of the valence electrons remain as non-bonding pairs. If we count those non-bonding and the electrons that an atom shares, you should end up with the number of valence electrons that it has. It makes sense. A different number means that the atom has gained or lost electrons, which is not likely. Technically, the formal charge is a separation of charge. In fact, some Lewis structures do require charge separation, but it is minimum as possible. Based on the electronegativities of some atoms, the element with the greater electronegativity will be the atom with the slightly negative charge. If the formal charge shows elements with large electronegativities as positive compared to the other atoms in the structure, we must question the validity of the structure. In calculating the formal charge, each electron in a proposed Lewis structure is assigned to a specific atom. The number of electrons assigned to an atom is then compared to the electrons that it should have in terms of valence electrons. If the assigned electrons and the number of valence electrons are equal, the formal charge is 0, because we're going to be taking the difference of those two numbers. If more electrons are assigned to an atom than there are valence electrons, it'll be negative because it somehow gained electrons. Similarly, if there are fewer electrons assigned to an atom than there are valence electrons, we can assume that it's positive and that it lost some electrons somehow. So calculate the formal charge, we simply look at the following. So for each atom, count all electrons not used for bonding by the atom, and then count half of the bonding ones, because remember, in a bond, each atom is contributing an electron, and they're shared together. So add steps 1 and 2 to obtain the number of electrons that the atom has in the structure, and then we subtract the assigned electrons from the valence electrons. So I like to, instead of dealing with this 1/2 business, what I like to do is just think of the number of electrons that the atom has contributing to the molecule, and then take a look at the valence electrons, and then subtract those numbers, as we'll see. So this is kind of it, the valence electrons. Instead of using this complicated way of saying it, just say electrons involved in the structure. All right. The formal charge calculation may be quickly checked, since the formal charges of an atom must add up to be 0, so that the overall structure is neutral. For a polyatomic ion, the formal charge should add up to be what the charge on the ion is. A molecule or polyatomic ion with the lowest possible formal charge, let's highlight this, put a star, is the one that's going to be the most probable. All right? So when do we use this? We could use it for a structure that is NOCl, for example. For example, which one is in the middle? We don't know. They all occur once, so it's hard to tell which one is in the middle. Chances are it's not the chlorine, because the chlorine needs only one more electron because it's a group 7. So is it the N or the O? We don't know. We don't know. What we can do, though, is figure out for NOCl, we know that there's one N, one O, one Cl, and nitrogen, it's in group 5, so that tells us, of course, that there are 5 electrons. O is a group 6, so it has 6 electrons. Chlorine's is 7. So 5 plus 6 plus 7. So we have a total here of 18 valence electrons. And you'll see in all these scenarios, we do have that. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. And you notice that all of these have an octet. 2, 4, 6, 8 for you, 2, 4, 6, 8 for you, 2, 4, 6, 8 for you. You'll see that they all work. So does that tell us that all of these structures are legitimate? And the answer to that is no, because we need to check the formal charges. So valence electrons, let's rewrite that as valence electrons, subtract electrons involved, I like to refer to it as, and we can get our number. So let's take a look at what we have here. So let's look at this oxygen. So no, oxygen, of course, it's group 6, group 6, group 6, group 6. So it should have 6 electrons, right? And nitrogen is group 5, so it should have 5 electrons, 5 electrons, 5 electrons, 5 electrons. And chlorine is group 7, so it should have 7 electrons, 7, 7, 7. But let's take a look at the number of electrons involved here. This oxygen, so half of these belong to the oxygen, or think of it like this. This electron is oxygens and this electron is oxygens, whereas this electron is nitrogen. So 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. The valence electrons that it should have, subtract the electrons it has in this structure, it works out. So good nitrogen. Nitrogen has 1, 2, 3, 4, 5. Guess what? That works. And chlorine, 1, 2, 3, 4, 5, 6, 7. Guess what? This first structure is good. That structure is valid. Let's look at the next scenario here. 1, 2, 3, 4, 5, 6. 5 minus 6 is negative 1. This doesn't look good already. This oxygen, 1, 2, 3, 4, 5. 6 minus 5 is positive 1. And then over here, 7 minus, I have 7 there. 1, 2, 3, 4, 5, 6, 7. Yeah, so guess what? That one's likely not valid. This one, 1, 2, 3, 4, 5, 6. Here we go. So already out of the gate, we're in trouble. 1, 2, 3, 4, 5. We get 0. 1, 2, 3, 4, 5, 6. So notice here that I have 0 plus 1 minus 1. So when I add these up, I get 0. But again, the valid structure should have all of them being 0. So that structure doesn't work either. And in this one, 1, 2, 3, 4, 5, 6, 7. Yeah, so right out of the gate here, we know that this one's not going to work. 2, 3, 4, 5. That's going to give us plus 1. 1, 2, 3, 4, 5, 6. Plus 1. So it looks like that structure there is the valid one because it satisfies the formal charge element of it. So I just did that right there. On the flip side, I have a chart here. The formal charges for oxygen here, you can see we're 0. Actually, structure 1 had 0 for all of these, so that is the legitimate one. Over here, the formal charge of oxygen was plus 1, nitrogen was minus 1, and chlorine was 0. Structure 3 here, we had oxygen being negative 1, nitrogen being 0, oxygen being plus 1. So that didn't work, that didn't work. And then the last one here, oxygen was plus 1. Nitrogen was minus 2, and chlorine was plus 1, so that structure didn't work either. All right, so that's how you set that up, using the formal charges to see, is that structure going to be valid? So let's look at this last example here. So draw the potential Lewis structure for the sulfate ion, and use formal charges to determine the best possible structure. If there is a best one, please do it. So SO4 2 negative. Okay, so we have 1 sulfur, we have 4 oxygens, and we have plus 2 electrons. So we have to include those 2 electrons added into there. So I'll just write it as plus 2. Sulfur and oxygen are both group 6. Right there, both group 6. So we have to write that as 6 electrons, 2. So here we get 6 plus 24 plus 2. So we're going to get 32 valence electrons. And I'm going to leave it there. I'll get you to draw the structure, and then in the next video we'll come back and take a look at that and see how you did. All right, we'll see you shortly.